Hello, welcome. This is Lecture 1 of MAT211, officially known as Calculus 2. In your earlier course, you studied the calculus of functions of a single independent variable. In this course, we will explore the calculus of functions of two or more independent variables. Let's begin the discussion with a three-dimensional rectangular coordinate system, also known as Cartesian coordinate system. In this system, we have three axes called x-axis, y-axis, and z-axis. They can be in any orientation. Here, we will follow a right-handed system. If you point all your fingers in the direction of the x-axis and then curl the middle, the ring, and the little fingers to the direction of the y-axis, then your thumb will give you the direction of the positive z-axis. This is called a right-handed Cartesian coordinate system. Throughout this course, we will follow this system. Any two axes of this coordinate system forms a plane. For example, the x and y axis forms the xy plane, which is the floor, and the x and z axis form the xz plane. Similarly, the y and z axis form the yz plane. Each of these three planes are called coordinate planes. Suppose we have a three-dimensional Cartesian coordinate system whose origin is O. The origin of a system always has the coordinates 0, 0, 0. Suppose we have a point P in space whose coordinates are A, B, C. It means to reach the point P, we have to start our journey from the origin O along the x-axis A units, and then we have to move along a line parallel to the y-axis to B units, and from here we have to move along a line parallel to the z-axis to C units. We will reach the point P whose coordinates are A, B, C. We will now discuss the distance formula in three-dimensional space. Suppose we have 2 points P1 and P2 whose coordinates are x1, y1, z1, and x2, y2, z2 respectively. To calculate the distance between the points, we first need to locate a point A which has the same y and z coordinates as of P1, but the same x coordinate as of P2. And then we'll locate another point B which has the same x and y coordinates as of P2, but the same z coordinate as of P1. Now a triangle P1, A, and B, this is a right triangle. Since we know the distance P1A, which is the absolute value of x2 minus x1, and the distance AB, which is the absolute value of y2 minus y1, we can simply calculate the distance P1B by simply applying the Pythagorean theorem. And then another triangle is formed by the points P1, P, and P2. Notice this triangle is also a right angle triangle. Since we know the length of P1B and we also know the length of P2, we can again apply the Pythagorean theorem to calculate this distance. So let's sum this up. So this distance is the absolute value of x2 minus x1. This distance is absolute value of y2 minus y1. And this distance is absolute value of z2 minus z1. So in the end, the distance between these 2 points is given by this formula as shown in the box. For example, we want to calculate the distance between the points P and Q whose coordinates are 2, -1, 7 and 1, -3, 5 respectively. According to the formula shown in the box, the distance is 3. Now we'll see an application of this distance formula. In this section, we'll begin our discussion with a sphere. Let's have a definition. A sphere is a set of all points in space whose distance from a given point C, whose coordinates are h, k, l, is r. Here the given point C is called the center and the distance r is called the radius of the sphere. We note that by definition the sphere is empty. We are just talking about the points on the surface. So sphere is just a surface and the center is not part of the sphere. Now we will see the very standard form of an equation in a sphere. As we said earlier, the sphere is a set of all points whose distance from a fixed point C is constant, which is r. So we can apply the distance formula here. So the distance PC is constant, r. And this gives this formula in the box. In particular, if the center of the sphere is located at the origin, then the equation of a sphere simply reduces to the equation shown in the box below. For example, we will show that the equation here is an equation of a sphere. We want to find its center and radius. In order to do so, we need to express the equation in its standard form of a sphere. To do that, we will rewrite the equation in the form of a sphere by completing the squares. Let's do that. Now we're regrouping the terms in the equation in this way. So in the first group, we'll have the x terms only. In the second group, we have the y terms only. And in the third group, we have the terms involving z only. And we moved this constant 2 to the right-hand side of the equation. Now to complete the square, for the first group, we need to add a number. For example, the number is 4. So we add 4 to the both sides of this equation. Similarly, to complete the square, in the second group, we need to add 9. And to complete the square for the third group, we need to add to both sides of this equation. So the first group simply becomes the x plus 2 all squared, and the second group becomes y minus 3 all squared, and the third group becomes z plus 1 all squared. And the right hand side simply becomes 16, which can be written as 4 squared. Now this is an equation of a sphere. If we compare this equation with the standard form, we see that the h here is -2, and the y here, means k here, is 3, and the L here is -1, and the radius is 4 units.